Should be good.
Okay.
Hello?
Yeah, you got some.
Okay. Our second speaker today is Katherine Kim. Katherine graduated with a BS in Electrical and Computer Engineering from Franklin W. Bolin College of Engineering in 2007. She received her MS in Electrical and Computer Engineering at the University of Illinois at Urbana-Champaign in 2011 and plans to complete her PhD degree in 2014 under Professor Philip Prime. Katherine's dissertation research is in power electronics, modeling, control, and protection for photovoltaic systems. She received the National Science Foundation's East Asia and Pacific Summer Institutes Fellowship in 2010 and Graduate Research Fellowship in 2011. She currently serves as the Student Membership Chair for the IEEE Power Electronics Society.
All right, thank you. Can everyone hear me? Okay, so this is a faculty talk, and it's going to be a little bit longer than half an hour, but what I'm going to do is I'm going to try to start or stop a little bit before the time is up, so 4:55, and I'll take some questions right then so that people can leave if they have to, and then if you're willing to stick it out with me, you can stay to the last part. So I'll take a break at that point, just for all of you to, if you have something scheduled. And I'm welcome any feedback. This is the first dry run, so if you have feedback after or questions that didn't make sense, I'm open to all of that. So with that, I'll get started. Okay, so I'll be talking about some of the work that our group has been doing on differential power processing and how that relates to photovoltaic systems and how we can use that to improve the energy lifetime, the energy production over the 25-year lifetime of a PV system. This work is supported mainly by the ARPA-E grant and also the Granger Center and the NSF through the Graduate Fellowship Program. Okay, so I would like to start with the, there we go.
Try that.
This is an example of a PV system in the wild, in the real life environment. This is my house in Marquette, Michigan, and usually you don't see PV pictures with snow all over them, but these are the realistic conditions that a PV system will have to endure over a 25-year lifetime. And I keep using 25 because that's the warranted lifetime, but systems can stay in place much longer than that. So we want to, this is my mom's house, right? So I want this system to be good for 25 years and to maximize the energy that you can get out of it. So with that kind of in mind, we're going to be looking at a few different things in this presentation. First of all, we'll look at mismatch and how that affects photovoltaic systems and how we are combating that. And the specific method we're using is differential power processing converters. I'll explain kind of the basis of that, how they work. And then we'll dig deeper into the research part of it and look at how we are using analysis to figure out their power ratings. And then with that, once we have a power rating, we'll figure out how much improvement we can get out of these systems compared to a conventional system. I'll also discuss briefly some future directions that I'm interested in taking, and then I'll wrap up. So first, we'll start with mismatch photovoltaic systems. So a PV panel is generally constructed with long strings, and we do this because each PV, and I say PV meaning photovoltaic cell, solar cell, so each cell is about half of a volt. And in order to connect these systems to a grid, we need a much larger voltage. So in order to do that, we have to stack them in series to get higher voltages. And if you see a large panel, usually they are, each column kind of goes, the string goes down and back up, and then there's a little junction box behind here, and all the connectors come together there. So taking that's a physical system. So you can always count how many cells are in a PV just by looking at its dimensions. This, for example, has 3 substrings, and you can see them here. I'm just representing each of them here. And each of these substrings has a bypass diode around it, but then each of them has usually 20 to 24 cells. So this is the most common number of cells in series for residential and commercial. So we have these in series, and because they're in series, they all need to have the exact same current. So we're going to look at how mismatch affects this. So we have, first we'll start with a very idealized string. So these are the IV characteristics, if you're not familiar with them. The voltage and the current. So the photovoltaic cell must operate on this line. And so if all these PVs are exactly the same characteristics, then we operate them at one string current, right? They're in series, so they have to operate at one string current. And we choose a maximum power point current, and they all perform perfectly. But this is unfortunately not very realistic. What happens is that if we have a cell that's underperforming, it's degraded, and they do turn this ugly color from the lamination on the top, you can actually see them kind of discolor and degrade over many years of operation. So say we have one that's degraded, we still only have one string current. We want to maximize the power out of the full string, but in order to do that, we have to kind of compromise. So the operating point for these cells now is no longer the maximum power point for these illuminated and undegraded cells. It's a little bit lower than maximum power point. For this one, it's a little bit higher, so it's kind of compensates between the two. You have to find a middle point. So if we have permanent damage, this permanent damage in the cell, we'll never be able to get that same amount of power from each of the cells. So this is why mismatch is such a big problem, especially when we have permanent damage. And if this becomes even worse, so, and also I'll point out what's happening between these two, all three of these, is see the current is dropping. What happens is that the cell is not able to, the same amount of illumination is hitting the cell, but it's not able to convert as much of the power into current. So the current characteristics go down, and that's why we get this shifting down in the IV curve. Okay. So this is an extreme case now. This is highly degraded. So these are all at the same illumination, but this is just not producing that much power. It's really degraded. What can happen is the other strings will kind of force it to go higher, and this will actually sink power rather than producing power. This is even worse because you're trying to get the most power out of the cell. This one is sinking power, these are producing it. It's not a good state that we want to operate in. We want to maximize the power from each cell. So where does this mismatch come from? We just did an example with degradation. But the more commonly talked about one in the literature is actually partial shading. Many people are familiar with that. You have an object shading your cell, you go and stand in front of it, an animal flies over it, an animal sits on it. Then that's where partial shading can come from. There's also things like dust accumulation. These are particularly a problem in dustier environments where you'll have like the panel will be a little flatter, and rain it's harder for it to wash away the debris. Other things as well. These are a little bit less extreme, but temperature differential. So one part of the panel is hotter than the other. You'll have some differences in the characteristics, and also pointing angle differences. So maybe one panel's pointing exactly at the sun, maybe one's a little bit off. So you have some variation in the light that's going into the cell. All right. We also have other types of variation called what I consider to be internal variation. So external forms and then internal. One is from manufacturing. So when you manufacture, you won't have a completely uniform PV system. Some of the cells will have different characteristics. That's an inherent form of mismatch. We'll also have cell degradation, used in the example earlier, and that will also create the characteristics to become more mismatched. So for the external versions that we just talked about, these are temporary. So you'll have shading, maybe in the morning, maybe it's just something that's covered the cell in fall, the leaves will cover it. They're difficult generally to predict. We can model them very intensely once we know what shading patterns, but we don't really know how often they happen over a 25-year lifespan. So because of that, it's very difficult to model over 25 years. So it's hard to say how much does partial shading really affect the system. However, the internal variation is permanent. So if this becomes degraded, it's going to continue to degrade the system for its whole life. And because of that, we can actually model it over its lifetime. So we're going to look at these two factors the most because we know where they come from and we can predict how they're going to change over 25 years. So let's talk about manufacturing first. If you ever looked at manufacturing or photovoltaic cells, you ever wanted to buy one for your house, you'll go to one manufacturer. This happens to be Suntech. I'm not trying to advertise for them or anything. They had a nice, really clear distribution. They try to make these look different, but I'm pretty sure they're exactly the same material. but they have different power ratings. They're all the same size, the same dimension, the same number of cells, but they have different power ratings. And when you look into the data sheet, it says it has a positive tolerance. So it's 0% or plus 5. So you can get up to 5% more is what they're trying to sell it as. But really what this means is that there's inherent variation in the panel. So if we assume that the distribution, so if we made a big batch of cells, we would get some sort of distribution. They all would not be exactly at one point. So this is extrapolated from those 3 PV panels that I just showed. You're going to have some variation in the distribution. And so what they do is they go through every single cell, and they bin them, they see how much power they can produce, put them into each of these bins, and then when they're constructing a panel, they take from this one bin, they make the whole panel. They do the same with the other ones. But what really, you could have one cell that's right at this power, you could have one cell that's right at this power, a few that's in between. So really you do have variation in that panel immediately from the beginning. So this process that they do to minimize mismatch is really laborious, it takes a lot of time, it adds costs, and it decreases the amount of mismatch, but it doesn't completely eradicate it. So even new panels will have some sort of mismatch between the cells. Okay? So now we've looked at manufacturing, what happens at the beginning, what happens over its lifetime. So we have a general degradation model, and not all of the cells will directly follow this trend, but generally you'll start at there's some sort of mean of all of the distribution. This could be in an individual cell. Most of the statistics are taken from large systems, so you have maybe 100 cells, or sorry, 100 panels, a very large amount. So you can get kind of a statistical variation. So you start out at some point, you have some variation, some sort of distribution here. And as the system ages, the cells will naturally degrade a little bit. And what happens is the mean will decrease over time. And this is, as we go up to, this is 50 years, this is an example. And the standard deviation, so the width of the distribution will increase. So in order to look at what we'll be doing in the rest of the study is we'll be looking at, we want a standard deviation of it at the beginning and at the end after 25 years. So we're going to use this information to kind of get a starting point and an ending point for our studies. So the way that this study defines coefficient variation is a little bit different than the standard definition. Usually it is the standard deviation over the mean, but in this case we are doing that same thing, but because we're looking at the rating for the full panel, we want to look at how we need to rate it according to the initial conditions. We're actually using the mean from the year 0. So this is like the rated power. We're going to look at how the variation changes over 25 years. So this is the definition we'll be using. So what are realistic numbers of that? What are realistic numbers for the CV value? Where are we starting? Where are we ending? We looked at a bunch of different studies. There's not that many actually that do a full 25 years. The best we could find is one study by Chamberlain who does 20 years, and this is in Humboldt State, I think, in California, a very long 25-year study, published in 2011. And without getting into the details of it, we kind of broke down how the standard deviation changes over time. And based on our definition, at the beginning of its lifetime, it had a coefficient variation of 0.23. And you can kind of think of this as a fraction, so if it makes it easier for you to understand, 2% variation based on the initial rating. And this was what it was after 20 years, 7.4. You have a hard time seeing back there. And then if we just do a basic linear extrapolation, we get after 25 years, we expect 0.86, so 8.6% variation. So now we have a starting point and an ending point based on a realistic study. All right, so if nothing else, we just have starting 2 different points to go from for variation. Okay. So mismatch is not good for the system. It decreases power. So let's look at different ways to decrease that, specifically differential power processing.
Can I just ask you one question about this 25-year study? obviously when you study aging over 25 years, you have to start with 25-year-old technology. Or at the end, it's 25 years old.
Yeah, so this is a little bit dated. Is that what you're trying to say? It's
Well,
a little bit
I'm
older?
just kind of wondering whether you have any comments on that, or if they're coming up later, that's fine.
I don't speak to that as much. I'll answer that right now. The technology the basic architecture actually has not changed that much in 25 years. It's generally a string of cells with the bypass diode. This study also used bypass diodes. The technology that's changed is mostly the cells have become larger and a little bit more efficient. But this could be a little bit more updated, but it's...
Well, you can't do a 25-year study except...
Yeah, but the technology...
Wait 25 years.
Yeah. Oh, okay.
Well, I think the important point is that silicon hasn't changed in 25 years.
Yeah.
And indeed, the processes have had just tiny incremental changes. It's been more about putting on the electrical contacts and packaging them than in processing the actual semiconductor. So a silicon photovoltaic cell made today and one made 40 years ago are not fundamentally very different at all. The differences are so slight. It's much more about how they get leveraged into the system. So that helps make this more representative.
So what are the sources of this degradation? To kind of like go off what Katherine just said, maybe the silicon hasn't changed, but the whole package of the module itself may have changed. So if like degradation is due to weathering or something like that, the whole module might be better at counteracting those things. So like, do you know what the physical reasons for degradation are? Maybe like new processes have helped prevent that.
Yeah, so I'll comment briefly on that. And the question, if you didn't hear, was what are the main sources of degradation in this study? Actually, one of them that was pointed out in the study was hotspotting, which is my other favorite topic of study. And so I think the point you make about the encapsulant is really important because once it becomes exposed to the environment, it does degrade faster. That's one of the largest things of increasing degradation is just being exposed to the elements. You get corrosion. If you're in a humid environment, it accelerates that degradation. So that may be a point that maybe just the encapsulants are better, so that would improve this. But we don't have we don't have a study to say this is a lot different. So because we really need the long-term study. So this is a representation. It can vary drastically based on the climate. So this is kind of our best guess that we can do and kind of go forward with that. Okay. So I'm going to continue on to talk about differential power processing. So how do we deal with, once mismatch is happening, what do we do to combat that? So the one way that is fairly commonly known in industry is to use DC optimizers. These are shown here. They're a DC-DC converter that connects to the PV. And this is usually at the panel level, so one PV panel, you have one DC optimizer, and it allows for independent control of the PV element. So if this one's degraded, all the power gets processed through here. The series connection doesn't affect it anymore. This has been a good solution up to this point. But one of the parts is that it processes all of the power. If this is producing 100 watts, this is going to process 100 watts. If this is 98% efficient, we're going to lose 2 watts from that. So all of the power has to go through the DC optimizer, and you'll lose some power from that. And this work has been done in a bunch of different places. It's been done for a while. So, and most of them work at the panel level, but some of the work, Professor Palala, who's here, has done it at the sub-module level, and that does increase the total power you can get out of it. Okay, so, but what we want to look at is utilizing the series connection. So if these are perfectly matched, all the power, why not have all the power go straight through here? And then, if this one's off a little bit, we can just power just the difference power through this converter and utilize both the series connection and the ability to control each PV at its independent maximum power point. Okay? These are sub-level devices. They allow independent control, just like the DC optimizers, but they only process a fraction of the power. They only process what the mismatch is. If everything's perfectly matched, it won't process any power. And because it processes less power, there are less losses, fewer losses, and you get a higher overall output. And this is work that we've done here. Pradeep Shenoy started it, and our group at ARPA-E is working on that quite a bit. And then also groups at Dartmouth, Jason Stout, their group is working on some things. Also a group at Boulder, Colorado, they're doing various things. So this is a really hot topic right now that is very promising. Okay. So what is this actually, how do we implement this? We have this idea of processing the mismatch. We have two basic architectures. One is the PV to bus, and I showed that a little earlier. It's shown here. Essentially, you take any power directly from the PV and you deliver it to the bus itself. So if this is 100 volts on the bus, this converter has to be rated to that 100 volts. And this side of it is rated right at the PV. There's another architecture called PV to PV, and it's shown here. And instead of connecting directly to the full bus, you only connect to the adjacent PV. So if you look at this one, only connected to this PV and to this one. So because of that, we're able to rate the voltages at a much smaller level. Also, this allows for us to kind of scale up. So if we want to add on 10 more units later on, it's not a problem to do that, where it might be a challenge to do that with the PV to PV. So we're exploring both of these architectures. They have various positives and negatives. And we'll see some of that, how it comes out in the rating in a little bit. How do we actually implement this for people who love power electronics? This is just a glimpse into the basic topologies we've been working on. So people familiar with the flyback, we are implementing that into the PV to bus topology. They utilize a coupled inductor here, and because you may be going up to a very high voltage, you can utilize that inductor current turns ratio to kind of make sure that your duty ratios are appropriate. For the PV to PV, we're using a buck boost type. Look at here, also called a switched inductor, which is this topology, and it enables us to bidirectionally pass power to and from the adjacent PVs. Okay. I won't spend too much on that. We're going to look at kind of the high-level stuff. So first, we're going to start with an example so that you can understand how it's actually processing the power in a bill system. So say we have 4 PVs, keeping it very small, and we have the nominal rating would be 50 watts, so 5 amps and 10 volts. And we have one that's kind of underperforming here, only 42 watts, and its current is lower, it's proportional. And we have one that's getting a little extra light, and it's producing a little bit more. Its total power that we can get out of the system is 194 watts. So what happens, the traditional, conventional way of doing it is to just put them in series. Let's see what happens there. Put them in series, we put some bypass diodes around them here. And remember, only one current can go through it. So the ideal current, and this is the IV curve, this is current on the bottom rather than voltage. So current here, there's one current that will maximize this full string, this point, and it's about 4.4 amps. If you operate there, you will get 183 watts, which is only 94.5% efficient. So right away, you're losing a bunch of power just from mismatch, right? Okay, there's no converters here, so there's no power being processed. Okay, so what happens if we implement VPP converters? We'll start with the PV to bus. So now we have these same PVs, and we are adding these converters on individually. You can see, in order to, so these are an amp apart. So this is 4.2 amps, this is 5.2 amps. So we need to add 1 amp, take 1 amp away in between this point and this point, right? So each of the converters can work to take away that amp. So this one takes away 0.8, and we're able to optimize each of them at their maximum power point. And this is the optimal point. This is the one with the star up here. This line here is the power processed through the converter. So we could force this line to be 4 amps, and these converters would work really hard to compensate all of that power so that each of them operates at the maximum power point, but we would have to process a lot more power. So in order the optimal point here is where we can reach maximum power point and we can minimize the power that's processed. So because of that, this is all the total maximum power. optimize. And then we look at this line and say, okay, this is the minimum point here. This is where we're processing the fewest power. And that's our output point. Okay? So here our output is 100%. We get perfect performance, but we're only processing 10 watts, which is 5.2% of the power. If we were using a DC optimizer, we'd have to use 100%. So it's a huge fraction of the power that we have to process. If we wanted to rate this converter for this specific example, we could say, I see it's hard to see, I see back there, sorry. The maximum current we need here is 0.8 amps. And if we base that on the 5 amp rating, 0.8 divided by 5 is 16%. So the rating here would be 16% for this specific example. Okay. If we do the same thing for the PV to PV, question?
So your power output out of the PV, not to like the downstream thing downstream like the inverter, right? I feel like 100% is sort of like a little misleading because you have some losses in your converters.
Right. This is all idealized, and we can take that into account. For this one, it's actually a lot easier to do. Yeah, I'm trying to do a one-to-one comparison, so we're doing the idealized to kind of show an upper bound of what we can do. This does not take that into account, but yes, you will have some losses. So this 10 watts you'll have some losses off of that. And then you'll also have some losses down the line. But if we assume the inverter is the same for all of them, then we're kind of we're trying to compare them directly. There we go. Okay. So we can do the same exercise with the PV to PV. And we get a similar thing. We're able to optimize these all. All of them are able to operate at their maximum power point. And if we look at how much power is actually processed, so we have something here again. We want to have an amp difference, and we have that. We have 1 amp coming in here, and then this current essentially brought back around. So we're able to compensate for all of the mismatch here. And in this case, we also achieve maximum power point. This one is the pink star here. Ends up being the same current, and we only process 8 watts in order to do this. Okay, so this is just to show how little power that we can process while achieving maximum power point with this architecture. Okay, if we wanted to, this would be approximately a 10% rating to achieve perfect performance. Okay, with everything being ideal. Okay, so next I'm going to do this again, but with a power rating of 8%. So that was with ideal performance. It can provide any current that it needs to in order to compensate. This is an 8% rating, so it's a little bit lower. It's not going to be able to completely offset the mismatch. So the maximum that it can provide here is only 4 amps. So if we do this and we kind of do the same thing again, we see that we get a little bit, this is the ID curve that it would be. We get a little bit lower performance, but it's 99.9% of the power that we could get is output, along with 15 watts approximately being processed. So you have to process a little bit more power, and you can get very close to ideal. Okay. We go on to the next one. This is the last one of this example. So we do the same thing with the PV to PV. So now this is limited. We're not able to provide any current. The maximum current we can provide through here, actually through this one, is 0.4, so the same current rating. And we get a little bit lower performance, so 99.9% of the maximum possible we could get out, while only processing 8 watts. So what we want to do with this system, so this was this one example, and this is one specific case that I gave you. What we want to do is look at a realistic system and say we have 15 panels and we randomly select the IV characteristics for each of them. How much power do we need to process? We do this exercise for very many cases.
Katherine, just very quickly, is this simulation or is this actual lab?
This is simulation. Yeah, this is all ideal as well, so it's simulation. Okay. So the 2 research goals that we want to do based on this analysis is determine the DPP converter rating that we'll need for 25 years of operation. So from the mismatch we expect at the beginning of life to at 25 years, we want to select a converter rating that is going to match the 25 years. And then once we have chosen those ratings, we want to be able to evaluate how much of an improvement we get from that. Okay. This is right about the time when people need to leave. So I'll take any questions right now, and if you have to leave, please do, don't feel bad. Techie people have to leave too, you have a meeting. If anyone wants to stay, I appreciate it, but you do not have to. Are there any questions at this point? I know that example might have been a little confusing. Carl?
That 3-panel example, how do you decide how you're going to optimize? How do you control it? Because I can see that's fairly easy to point if you extrapolate it to 48, that becomes a bit more challenging.
Right, so one of the things that we are doing in the simulation is assuming that we actually know the maximum power point of each panel. So typically you would use a maximum power point tracker. In this case, we're not doing that. I'll actually go to, this is a simulation that will be ran at. And so there's two assumptions we make is that we know they're ideal converters and that we already know the maximum power point. So we're able to know to operate as closely as possible to the maximum power point. It's all done by calculation.
So it's more based on kind of what the normal cell in the system is, as opposed to measurements.
Yes, yes. Everything's simulated in model.
So it's in the real world. You're going to measure performance, and then that's going to determine how you control.
Yeah, in the real world we have current and voltage measurements, and we would do a maximum power point tracking to try to achieve that, and then within the bounds of the converter's rating, you would operate within those bounds.
And that's based upon for a single idealized panel. You don't control them against each other.
I'm actually not sure what you mean, but maybe we can talk offline after. Okay, thanks. Okay, so I'm going to continue on. This is where we actually look at how this actually turns out. So we have the one example that was maybe a little bit confusing, but we'll be looking at the statistical results. So what we did is we took, rather than the 4 PVs, we looked at 5 PVs, and this is equivalent to 5 panels, and each of them would have 3 sub-panels. You can kind of see that shown here. We're doing a Monte Carlo simulation. So we're taking the 25 panels, we have a Gaussian distribution of what they should be. Based on our CV0, we found that distribution. We randomly select those PV characteristics, and we actually go from a variation of 1% to 20%. And we do, I think it's 100 sets, it might actually be 500 sets, at least 100 sets at each of the 0.5. So we're kind of looking at every single increment as we increase the distribution, how much power is produced in each of these converters, or how much power is processed through each of these converters. Okay, so using this, first we want to define, our first goal is to find out how much power do we need? What is the rating of the DPP converters in order to perfectly offset the mismatch? Okay, so we have a sweep of the variation, so we're increasing the variation between these panels. And we get a distribution of results because it's a Monte Carlo input, we get a distribution out. And we plotted that over the, up to 0.2 is 20%, same. You can use that interchangeably. And we want to look at what it looks like at our expected CV of 25. We said it was 0.086. So this is our point where we expect it to be at 25 years. So you have a distribution, and in any distribution you have a median point, right? And then you can get 75 percentile and a 25 percentile. So it's hard because there's so many points to visualize this, but this point's the median, and this is the 75 percentile, is 25 percentile. So based on that, we can say, well, if we're kind of expecting a median performance, we would need our rating to be 17%. So 17% power rating based on the PV power. So if this PV element is 100 watts, this converter, if we want median performance, has to be 17 watts. Okay? So that's what we expect we would want. We're also going to look at a little bit above and a little bit below. So 22% rating and a 15% rating. Okay? So we do the same thing for the PV to PV. And you'll see that the distribution widens out. So because these kind of lines spread out and went up. We have a little bit larger distribution. So the PV to PV is a little bit more variable. We're not exactly sure how it's going to react. And these are based on the exact same inputs. So all the data points are exactly the same for each set, so you can compare them directly. Same thing again, but we find that if we want 25-year performance, we'll have to make these converters a little bit higher for the PV to PV converter. So 23% if we want medium performance, up to 33% if we want even better performance. If we want to kind of cut it lower, we do down to 18%. So with these converters ratings in mind, we actually want to, okay, actually I'll back up. This is for 15 PVs in series. But that's a 5 PV panel system, but you may want a larger system or you may want a smaller system, right? So we did the same exercise, and based on this point, so medium performance at 25 years, we looked at how does the number, if we increase the module size, what is that recommended rating, how does it increase? And this is really interesting because it actually shows, so this is the PV to bus, and this is just a kind of general line fit. As you scale up the PV to bus, so up to 60 modules, PV elements, the converter rating will increase, but it kind of levels off. So maybe you need a little above 20, 25 power rating, but for the PV to PV, you actually, it's going to scale quite a bit more. So if we keep scaling up and up and up, this system for the PV to PV is maybe the advantage of having a small power rating is not as advantageous at really large systems. So this is an important metric for how large you think your system is, which converter size you would want to choose. Right. So
why would that be? I don't understand why you wouldn't get that advantage in larger systems.
It's because we've done some simulation work on this in the RV project, and it mainly has to do with the fact that you're double processing power with the PV to PV converter. You can only process power from around your two adjacent elements, and as this goes up and up and up, if you want to, this one needs extra power, it has to come from this converter, and that power converter gets power from this converter, and it scales up. So if you have a really large system and you have pretty significant mismatch, it's actually maybe not the best quality for that. So that was an interesting finding that we had to do this work. Okay. So we have two general values that we've chosen. We have approximately 23, I think it's 15, so 23% rating for the PV to PV and 17 for the PV to bus. So using those ratings, we're now going to say, okay, so this was all assuming ideal performance or perfect mismatch compensation. What happens if we limit the current that it can provide for the PVs? Okay. So this is now where we look at how much improvement do we actually get once we select these values. I'm going to define a general improvement figure of merit, and this is just a way to say, compared to our baseline, how much are we going to improve? How much better is this system than our baseline? Our baseline is a series string power output. So if we just put them all in series again, what do we get? And then compare that output to what we're getting with the DPP converters. This gives us a sense for how much we're increasing our power. If the figure of merit is 1, it's exactly the same. If it's above 1, it's a better performance. Okay, so we looked at this, looking at just the PV to bus first, so this topology. And we have the 3 different sizes that we found earlier. And this is as we increase the variation between the PVs, how much of an improvement do we get? So at very little difference there's very little coefficient of variation, the DPPs don't really provide that much of a benefit. It's almost exactly the same. But as they become more varied, the improvement over that string is actually going to increase quite a bit. And what we care about is the improvement between our starting point, CV0, and our ending point, CV25. This kind of just shows if you have more and more variation, you're going to have an even bigger improvement as you increase the coefficient of variation. Right, so we get a similar thing for the PV to PV, a little bit more of a dispersion between here. But again, we only care about in between these 2 points. So it looks like, so go back to this one, for the PV to bus, 15 actually might be good enough. So 15 to 17 is kind of the recommended value for achieving near optimal performance in our expected range. And then if we look at the PV to PV, it's a little bit, if you calculate this out, it actually ends up being really similar. So the 23, or oversizing a little bit, 33% is actually a recommended range. So you have to kind of oversize the PV to PV a little bit, and you can undersize the PV to bus. Okay. Actually, I skipped this one because I think I don't need it. Just to show what the distribution looks like. So before we were looking at just the median performance. So here we're actually looking at the median point. But what does this actually look at like? So this is at 25 years. So we did just 25 years and we looked at the distribution. We looked at the improvement figure of merit and how much it changes. And so here you can see, this is kind of the median is I think at 1.06. So it's actually a 6% increase on the median. So median 6% increase over the series string at 25 years, which is actually pretty significant. If you're, after 25 years, you're still getting 6%. If you look at it over the full lifetime and you integrate it, it ends up being a 2.8% increase over 25 years of operation. It's pretty significant. It's very similar for this converter. So we can kind of, these are generally the converter sizes that are appropriate. 15 to 17 and 23 to 33% ratings are about appropriate for this size system. So the findings that from this research is we identified CV values for that starting point and that ending point. We also picked 15 to 17% converter rating for a PV to bus system, which, and remember this is compared to 100% rating on a DC optimizer. So that's a significantly smaller converter size for essentially equivalent performance, actually a little bit better because you're not processing all of the power. The PV is a little bit higher rating, but still much lower than 100. And if you kind of sum up it all up at 25 years, on the median you'll get 6% more power at 25 years, and over the whole lifetime, 22.8% more power. Okay. Is there any questions on this part?
More perks.
Sorry, there are. We can skip them if you guys want. It's future research directions, so it's fun.
No, it's
Go ahead, sorry.
25 years is a really long time.
Yes.
So trying to compensate for degradation in the panels, what happens to all the additional switches and electronics which added on over 25 years? Is there a assumption about the failure rates that
That's a good question. So,
part B?
okay.
So you end up with the 2.8% increase in energy.
Yes.
Is that a large number to you or a small number? How does it?
It's large. Well, I guess I'll answer part B first. So it's a large number because it's over 25 years. This is average or integrated overall of it. So if you can get, if your system is, a set number for 25 years, you increase that by 2%. That can be significant.
Compared to the cost of what are we adding?
Well, that's another very also great another point. If we can implement this for under 2% increase compared to DC optimizers, then or in traditional systems, then you're essentially paying back. So as long as the cost isn't more than 2% of the power cost, then you can even out and even get more money out of it or more power per dollar. So that's an important goal. If if this costs twice as much as the normal system, it's not really worth it to implement it. But we've been looking into ways to really sizing down the electronics and all of any additional things we'll need in order to implement this. And the first question about the ratings and degradation over time, with DC optimizers, you're processing all of the power immediately, and you're constantly processing that power. With DC or DPP converters, it would initially only process very little amount of power, and over its lifetime, it would start to process more and more power. So if it's a wear and tear kind of degradation, it wouldn't actually set in until later. So it actually would be much better than the DC optimizer system, which are already in use today. So you still have some faults that are going to happen, but it's not any worse and a little bit better than DC optimizers. Okay. It's only a little bit more. Oh, sorry, Chris.
Okay, so you say PV to bus can be rated at a smaller value than PV to PV, but the PV to bus are 5 based, right? They have to be. So
I don't have to be, actually.
They don't have to be.
Well, if you're, it depends on the size of your system.
Okay.
Yeah.
Because I was going to say that knocks off significant efficiency. I mean, it takes a significant efficiency toll right there, right?
Right.
Is that,
The flyback is just a lower efficiency.
so like, would these tend to, would you just back of the envelope in your mind, would you say that these kind of even out in terms of power savings?
They might, and this is a direct comparison of the idealized results, so it does depend highly on your topology and what efficiency you reach, and I left that out of here specifically so you could compare. So yeah, that's a good point. It might come back out and be about the same. And I think we're looking at, you know, like if you want to be safe anyway, you would oversize these, so you'd be at 30%, 35%, like that. So it might not make that much of a difference, but at least we know how much they should be sized, ideally.
A question, like, when you couple this 2.8, you assume, for example, insulation is just perfect.
We're
So if
assuming
you-
there's nothing.
Like, no, I'm
Yeah.
saying, like, for example, if you consider the change in weather, like the insulation pattern, you can definitely get more than 2.8% increase.
Yes. Well, it depends on, because it'll start to go to the edge of the ratings. So once we hit the rating limit, it'll actually not do well in extreme conditions. But I stated this earlier, it's just so hard to figure out how much of it, when is it partially shaded? Is it 1% of its lifetime? 0.05?
But I'm saying, like, it definitely should be more than 2.8. Like, if you
It
take
could
that
be,
into
yeah. This is a bit, a little bit conservative, so.
This is just a permanent mismatch savings. Like
Yeah, this is-
degradation. But you said it could be on top of that, there could be extra energy savings from the clouds.
Yeah, so if for, you know, little mismatch we can compensate for, then there could be.
So
Of course, it's not like the ultimate number. This is, of
Yeah,
course,
but
for
you think this is
install.
the big part, or is the other temporary stuff the short?
I think this is extremely important because it's permanent. So, you know, it changes, it's not coming back to its other point, whereas temporary, it'll get shaded and come back. So you're only, you know, and those are usually very short conditions, where this is over 25 years. So, okay, I'll talk briefly about some future ideas I have, and I hope you think they're interesting. I'm welcome any feedback on this. So I've been working on photovoltaics for 5 years, and kind of thought about what other areas might be interesting to implement them. And I thought that photovoltaics or power electronics for mobile PV applications is an area that's growing and has been explored as much. So for example, the two things that areas of interest are, one is the PV powered hybrid and electric vehicles. This is the new concept car that Ford has come out with, I think at their Consumer Electronics convention or whatever it's called, not too long ago. And so the idea is to put, you know, panels on top of your car. You're outside anyway. You're moving around. Why not get some extra energy to recharge your electric vehicle? Or if you have a hybrid vehicle, add a little bit of extra energy, not just from regenerative braking, but also from PVs on your roof. So that's one, you know, general application area. Another one is PV-powered wearable electronics. And this is kind of, I think this is an Australian Army person, and they are, you know, sporting some really good-looking PVs integrated into their clothing.
Kind of defeats the camouflage purpose.
That's true. And I like this because this is kind of, if we said, you know, put PVs into your clothes, you'd be like, okay, I'm going to put these on me and walk around. And so maybe this is, you know, the early implementation of it. But maybe in a little bit, we'll have much more sleek versions of PV integrated clothing. This is, I don't know if this is actually produced, this is a concept at least. These little fun designer squares are PV cells, and this is, I think it's conductive thread. So you can make a very fashionable solar powered bag. Maybe you just put your phone in there and it automatically powers as you walk around. So this
Capacity factor would be kind of low on that unless you're like,
I mean, yeah.
I guess if you're working as construction.
Right, so, and people have those backpacks you've seen. So it does make sense. You want to have them in places where they're going to get light, not in an indoor application all the time. But these are just kind of different ideas that open up new ways to power things. However, there are some challenges with integrating PV into these kind of moving applications. The biggest one is uneven illumination. So this one has different angles, this one has some curve on it. You're gonna get some different angles. You're gonna get shading, angle differences. You're driving through downtown, you're gonna get some shading happening. There's gonna be some temperature gradients, maybe, all the different things. We already learned that series string does not do well to handle mismatch. So what are we gonna do there? We're gonna do DPP, but I'll talk about that another one. Illumination. So we have the transients are happening. We're driving through wherever there's, transits up and down, and they're extreme changes and they're very frequent. And traditional maximum power point factors that are used in large PV systems are really slow. They're really slow. They're actually made extra slow. And sometimes if like a bird flies over a PV system, it'll actually shut down the system because it thinks that the system is losing power and it'll shut it down and have to reset it. So these maximum power point factors are pretty slow and not very efficient for fast transients. So ideas I have for implementing
you should probably add to that, since you're doing this as a presentation. Capacity factor is an issue because you look at capacity factor, you cite it in the best location you can, then you put it on a car, and maybe the car is parked outside in the sun, wonderful, but a lot of times it's not, or it's in a covered garage, or it's in your garage at home, and it just goes down. And then to tie in how cruddy the winter is here in Illinois this year, you can say, if you look at a lot of cars out there, they're like coated in brine because. So
that car too is made to go with a solar multiplier that is a lens that increases while it's parked, increases the sun 4 times. And I thought, what's a car inside? If you leave it out in Southern California during the summers, what if you increase that heat 4 times to like charge up the battery to 75% of driving during the day?
How does it get more?
It's a big
It's
lens.
a higher, it is more efficient, it's concentrated PV, so it is more efficient if you put a whole bunch of irradiance into it, but it also makes it hotter and it can degrade. So
And you gotta, at your job, you'd have to have that lens if it was there during the day to charge it up. So I don't think they thought it through too well.
Smaller, but the whole, you're only the roof area.
It's a trade-off.
You're like sitting on your roof. It's like giant.
Yeah, everything inside would just start to melt.
All right, so this is clearly there's many things that we need to think about, but I think it's an interesting area. And what if we can enable this, bringing photovoltaics into a mobile application? And maybe we have to figure out, is it cost effective? What do we need to actually do to make it happen? But I think it's an interesting space that can bring up a lot of different opportunities and maybe change the way our society runs. So one idea is to use CVP. I won't go into it, but actually put them in parallel. That's better for PVs themselves. Series don't do well. Trying to explore these kind of architectures and see how they integrate into things like vehicles. And also looking at irradiance changes. We know how they change under different irradiances, so we can look at specific control architectures. Specifically, one that I worked on for my master's, the voltage offset resistive control that actually does very well for very quick transients. So utilizing those kinds of things. Quick thing, just to wrap up everything. What we've looked at in this presentation is looking at the PV values, the coefficient of variation values we expect over 25 years. We went through the whole procedure we went through is a procedure that can work for any size PV. We can look at 5, 10, 15, larger than that to figure out an appropriate rating. We found appropriate ratings of 15 to 17 for the PV to bus converter and 23 to 33 for the PV to PV converter. And we looked at some exciting new applications of DPP converters and control in mobile PV applications. So thank you very much for staying. I appreciate it. Any questions or comments or thoughts? Or you can go.
One thing I do wonder about that CV value, and you can't address this necessarily, but we all know manufacturers, when they're in a cost competitive business like PV panels, they try to make their products as cheaply as possible because they gotta compete on price. So sometimes there's a quality trade-off, and you might look and say, well, 25 years is a long time in the future, and you make trade-offs, and you might sell panels that degrade faster. It's theoretically possible. It's not the silicon necessarily, it's the
So a lot of times
connectors or this or that. I mean, it's hard to say, and nobody wants to kind of address it necessarily, but they're competing on price, and you go into Walmart and you don't always get the top quality product.
Yeah. It's actually, it's a very saturated market, and they're really for low prices, so, yeah, that's a good thing. Another thing? Yes? Go ahead.
Doesn't really have much to do with your presentation, but I'm just kind of curious. What does your mom do in the winter when there's snow on the panels? Does she like?
No, I think it's actually really dangerous to go up on the roof. Like some people shovel off their roofs, but usually they're really angled really high. So they've given me like no power right now. I actually I can look at how much power each of them produces. Like the end ones are producing no power right now. So they're not getting a return on their investment right now. It's not good. But
Where do they live at?
Marquette, Michigan. No. Because a lot of snow. It's right on Lake Superior. But they were the coolest house on the block because they have TVs.
When?
Oh, thank you so much. Next week. Yeah. No.
Kevin, are we all set for tomorrow?
Yeah. So could you just run power to the panels back and warm them up?
We're good, Kevin?
That's a good idea. You're good, actually.
Yeah.
Oh, thank you very much. Everyone got lost. I can tell.
Hey Carl, how you doing? Okay. I hope the engineering open house guy was making a big deal about moving stuff for EOH. You know, there's EMP page that weren't exactly sealed it, but it's like, I don't think it could cause any damage. Well, that open motor, actually, it was the one that was down here, but it's upstairs now. For the 3 days, we had the different rotors.
Because this one either takes out and then
That's such low power, you can't hurt yourself.
I know, but with some.
I know.
Looking at it now.
Last year they called us on it.
Did they
And
say?
we looked at the exact same thing, and we said, damn, this is like.
You can just grab it and stop.
You can touch it with if you touch it with your finger, it'll stop. And that was kind of.
So then they just.
I can't remember who had your position last year.
you can.
Yeah, Raj, she wouldn't fix it.
It's kind of in between.
I think I wrote something.
But this one is where
They
this
said
one
this is
connects
a
from here
ridiculous
to the bus.
thing.
Yeah,
because
and then
it's
this one is kind of
so low
the other
power.
extreme where they don't
But there's
connect
no
to the
end.
bus, they connect to each other. You can do
Everything
it